Okay, hi guys, welcome back to the wireless channel. I'm Niklas, and today I will talk about a nice little paper that I presented last year at the Asilomar conference, which is about discrete aware matrix completion via convex-sized L0 norm approximation. And this actually also covers some part that Professor Abreu already hinted at one of his first videos. And of course, this was again a collaboration with Continental. So let's start by some nice and easy introduction to the concept and idea of matrix completion. So for the most well-known example is just a movie recommender problem. So in the table here, you can see you have some users 1 to 4 and you have some movies 1 to 4. And every user can rate the movies, but you can see some of the ratings are unknown. So not every user, of course, rated every movie. But you can also see that the entries are discrete, which means, for example, in this case, the reviews are scored from 1 to 5. And now the question in this problem is, how can the matrix completion optimization problem, so filling in these unknown spots, be solved over discrete sets or finite alphabets? So by knowing what the value should be in the end. So in this case, 1, 2, 3, 4, or 5. Then before we go into our method, let's look at some classical formulation of the matrix completion problem. The most straightforward example is always the original rank minimization problem, which is an NP-hard problem that you can see here. So we want to minimize the rank of the matrix X, which is the desired low rank matrix, with the constraint that the values that you already observed in the matrix O, so O is the incomplete matrix, should be, of course, in the end, the same as the ones that you complete. So in the end, the observed values should be the same values that you have in your optimized matrix X. And then what you can see here, omega are the indices of the observed data, and then the p omega is the mask operator, which gives you the indices of the corresponding values of the set. Then now the rank operator is, as written here, an NP-hard problem. So what we can do, we can relax the problem using the nuclear norm, which is the tightest lower bound of the rank operator. And then this just leads to changing the rank to the nuclear norm. What can we do next? Next, we of course have to also relax the constraint to include some errors in the measurement. For example, if you measure the observed matrix, there could be some errors. So what we can do, we change the constraint that we say, okay, there could be some error in the measurement, which is now denoted as this epsilon. And then the constraint we define as f of x, where we now can change the optimization problem, rewrite it into a regularized problem, where we now have just minimizing f of x, which is the observed data with some errors, plus the nuclear norm. Next, we come to our previous contribution, which is the pure idea of the discrete array matrix completion, which was proposed by a former student of Professor Abreu, Imori, which was also a paper submitted to Asilomar in 2020. And this idea starts by, okay, now we have the well-known matrix completion problem, so f of x plus the nuclear norm. But now our entries of the matrix X are not in the real, of course, they can be in the real domain, but now they are in this alphabet set A. So let's look at the problem. Now we assume we have a finite and discrete alphabet set. Give it A here. We can have A1 to, depending how many values can be in the matrix. And then this can be generalizing the optimization problem by just adding an additional regularizer, so an additional term, which is now here the Rx given P, which is the discrete space regularizer. And how does it look? It's really just another term that penalizes your optimization problem if your values that you put in X are not part of the discrete set. So you go through all of the values in A, and you check, okay, are the values that I want to optimize for in X part of this set given here in AK? And then for P, this is saying which norm we use, which should be optimally the L0 norm. But in this paper, to keep it simple, we first start by using the L1 norm. And then also just for completion, this omega bar is the complement set of omega, so not the values that you observed, but the values that you did not observe. So as I said, in 1, we relax the problem by using p equals to 1. But the problem now is that Rxp is convex, but not differentiable. So what was done to solve the problem? We can use this proximal gradient solution. Proximal gradient is just some gradient descent method, but this is used in optimization problems where your different terms are mixed between smooth and non-smooth functions. So if you look at the problem before, we had some smooth and non-smooth functions, so we had to split the problem. And now this can be solved iteratively via proximal gradient. The first step is the so-called momentum acceleration. This just accelerates the convergence of the problem. The second step is the proximal gradient method, proximal gradient step on f of x and the discrete space regularizer, which you can denote here by this proximal operator on y of t, which y of t you get from the acceleration. And then the third step is just a singular value thresholding on the result of step 2, which is meant for the nuclear norm part of the optimization problem. So now step 2, the proximal gradient can be solved in the following way. So you have this proximal gradient operator for RYT1, which can be formulated in this way. So you have your part for the discrete space regularizer and for the f of x. This can now be vectorized and rewritten as you can see here. So here we were working with matrices. Here we now only work with the vectorized form, which you can see at the bottom. And this can be now solved element by element wise. And it was shown that actually, if you rewrite the problem element by element, you get this formulation. And in the end, you get a nice closed form solution, which can be obtained, given here by ZT bar. And finally, the only step you have to do now, you have it element by element. And in vectorized form, you have to, of course, bring it back to the matrix form, which can be done by the last step. So we can recover the matrix ZT and move on to step 3, which is the update via the singular value thresholding function, which you can see at the top. It is simply a singular value decomposition, which you can see here. So A can be decomposed in U, sigma, and V transpose. And then this thresholding is just thresholding this decomposition with a factor of lambda. And this parenthesis plus is the positive part of the input. So now we have solved the discrete aware matrix completion problem. We have some nice features, which you will also see in the results later on. We have low complexity, we have fast convergence, we have large gains over the state of the art. For example, we have here some examples of prior matrix completion methods. We have soft impute, inexact soft impute, and then also non-convex inexact proximal gradient. But the problem is, if you remember, we relax the norm of the P to be a L1 norm, but we can do better if we use the L0 norm. So what we did in the more recent paper is now we did the discrete aware matrix completion via L0 norm approximation. So first, what is L0 norm approximation? If we just look at an arbitrary tried, so L0 norm approximation is an arbitrary tried approximation for the L0 norm of a vector x of length L. So you can see here, you have your value x, you have the L0 norm, and this can now be approximated by the sum from 1 to L. So you have all your values. You have xi squared divided by xi squared plus alpha, where alpha is this small constant, and this can then also be rewritten, as you can see in 1, where you can stop the video and check for yourself. So this goes to 0 if this part is 0, or it goes to 1 if this part is greater than 1, which is exactly what we want for an L0 norm. And to show it a bit more visually, we have this nice figure here. So in the middle, you would see the actual L0 norm, where you have a value of 1 here, and here it goes down, goes up. But now if we use the approximation for different terms of alpha, we have 10 to the power of -3, -2, and -1. You can see the approximation. And now this is, of course, arbitrarily tight. But as you can also see in the figure, this is not convex. So what we have to do next is first we can apply this to our regularizer and then make it convex so we can solve it. So first we can apply the approximation. You can see now we put the 0 here for the P. So you write it here, have your regularizer. Then you can write it element by element. And then next you apply the approximation where, like we showed before, you have first your first term depending on how large your vector is. But this is a constant, so we can ignore it. That is left for the regularizer. Then what we can do next, we can just skip this part, write it here, and then say, okay, this is now our tilde. Yeah, good. Then the next step is now, as I said, it's non-convex, so we have to find a convex size reformulation by now using this well-known method of fractional programming. So we will just summarize it here. The details can be found in the paper. If you look at the regularizer again from before, you have this term, and this can now be rewritten by using fractional programming in this form, which we call h of x, where h of x can also be rewritten again by all of these vector formulations of the matrix you want to find x. And then also this B matrix and the small b vector, which can be found by the fractional programming constant, which is defined actually by the constant of the L0 norm approximation and also the value xi. Now that we have everything defined, what we can do next, we can look at the complete optimization problem again. So again, we want to minimize. We have again f of x, which was here depending on the observations. We have now h of x, which is what we found before. And again, we have now we call it g of x, which is our nuclear norm. Now here we have also, because we need later on, the gradient of h of x, which can be given by equation 8. And what we do next is, before we solve it, we see, okay, now this has some nice features. It's convex and it's a smooth formulation. So it's easier to solve, and we only need 2 steps for the proposed solution. First, we have the momentum acceleration again, and then we just need one singular value thresholding updating step, which is shown in equation 10. And then finally, just for the sake of completion, we can note that the step size mu can be found by the so-called Lipschitz constant, which is computed as shown in 11b. Now to look at the full algorithm again. First of all, the input is, of course, our incomplete matrix O and the constants alpha, lambda, gamma, and psi. Then first we have to initialize the matrix X with some random matrix, which was needed for the moment acceleration, if you remember again. And then we have 2 loops. The first one is until the convergence of B, where B was given by the fractional programming stuff. And then the second loop is until the convergence of the gradient algorithm. The steps again. In line 3, we first compute the capital B matrix and the B via equation 6, which was defined by the betas. Then we find the step size via equation 11 by the Lipschitz constant. Then next in the loop of the gradient algorithm, first we compute x of t via equation 9, which was the moment acceleration. Then we compute the gradient, which was found by equation 8. And then finally we can do the updating step to find xt plus 1 via equation 10, which was the singular value thresholding. And then this is done until convergence, and you have the completed matrix X. Now to look at some numerical results, what we use for the evaluation is the movie lens 100K dataset for comparison, which is available online and is a very common dataset to compare matrix completion algorithms. And then the performance was measured in terms of the NMSE, normalized mean square error. Then first, what do we look at now? We have a comparison with a varying ratio of observed entries in O. What does that mean? If you have here on the left 0.2, that means that 20% of the entries of the matrix O were observed, which is increasing up to 0.6, which is 60%. 0 would be you didn't observe anything, 1 would be you observed everything. but we look at this nice middle here. And we compared the following algorithms. We first have the soft impute, then we have the AIS, which is an accelerated version of the soft impute. We have the original discrete aware matrix completion algorithm, where you can see we use the L1 norm. And then we have the proposed version with the L0 norm. First, you can see that the soft impute methods both have the same performance, but you can see a large gain if you only use the relaxed version of the discrete aware matrix completion algorithm, which you can see here. And then finally, as we were thinking, if you now use the L0 norm approximation, you get another additional gain, which you can see here between the black diamonds and the red balls. Now this is for the numerical results, and now we can also compare it for the convergence behavior. Now you can see that the slowest one is the soft impute. Then if we look at the accelerated version, this one is faster, but if you remember, it has the same results, but it's faster. Then we have a proposed method, which in the end has a better performance, but converges a bit slower. And then finally, we have the original discrete aware algorithm, which is slightly worse than the red one, but converges much faster. And this was done for 20% observation ratio of O. And then finally, one thing that we were thinking is, okay, what if we first start the process by using the relaxed version of the algorithm because it converges faster, and then we switch to our proposed method? Will there be a gain? And this is shown here. We have now the convergence behavior of the proposed method, which is initialized with our initial method for 25 iterations. And you can see indeed it converges really fast until 25. Then there's a small spike because we switch to our proposed method, so it has to adapt first. But then it converges really fast to a really low level. And this was also shown for 20, 40, and 60% ratio, so it works for all of them. Yeah, okay. Thanks for the attention. That was it. If you have any questions, feel free to ask.
Thank you, Nicholas, for the excellent talk. I have one question, perhaps a comment, which is, have you considered any alternative to use the nuclear norm minimization in order to force the low rankness of the solution? I know that nuclear norm is the standard approach, but perhaps there are other alternatives. I just wonder if you had even considered that.
Yes, very good question. You can see here also, so we did it for this convex version of the nuclear norm, and in this case L0 norm or L1 norm, but it could in theory also be done for non-convex versions where we don't use the nuclear norm, but other alternatives that are, but then in fact non-convex, so we have to solve it in a different way. But yes, it's possible, but we didn't look into it yet.
Okay, thank you. Anybody else? Any other questions?
So I have a quick question. Could you go back to the first result that you had for the performance? So from what I'm seeing here, the gain just by doing the L0 norm as opposed to the 1 norm is actually, it actually converges, right? For example, at 0.6 ratio, you almost have this with both the L0 and the 1 norm. So that means if the number of observed entries is higher, then the performance actually is kind of the same, right?
Yes, exactly.
So what I'm wondering is it worth doing this? So what's the trade-off? Does the L0 norm, by doing the fractional programming part, do you have some additional complexity that you need, or is the L1 approach, I don't know, of low complexity? So because if this is the case that both of them converge at for example a high ratio, then is it really worth doing the L0 norm here if it's more complex than the L1 norm? You know, that's my question.
Yeah, good point. So yeah, you're right. You can see here for 0.6 and beyond, the performance will be nearly identical. And then also if you compare it with the convergence behavior, you're right that our proposed method, so the L0 norm approximation, is quite a lot slower. So I would say, depending on your application, if you know that your ratio of observed entries is really low, then and you want really good results, then you should go to the L0 norm approximation, which, okay, yes, it converges slower. If you want, as I showed, you can combine the two algorithms to make it converge faster. But yeah, so if you know that your ratio of observed entries is higher, you can just go to the relaxed version, and the result will be the same.
Okay, thank you.
Any other questions, guys? If not, thank you very much again, Nicholas. We can close this, and yeah, I see you in the Wireless channel next time.